Well, welcome back, everyone. We'll get going in just a half a minute. And we're there. Looks like we can start. Welcome back, folks. So we're on week 3 of the course, but this is only our second full entire week since we had Monday off. Canvas might look a little strange to you. It looks like we didn't do anything at all in week 2, but things move around in Canvas. I moved the chapter 2 material down onto week 3, since that's the week we're actually completing that work. We're on the last example, so not much to do into chapter 2, and we'll be moving directly into the normal distributions, chapter 11, once we finish off the notes there. Also, assignment 1 has been graded and returned. This is the first time for me personally using the Canvas homework system to return and accept homework. So let me know if anything goes wrong there. If you don't have your graded homework returned to you or anything like that, reach out. I have the file and I'll be happy to send that information. Also, the course is just getting started. One noteworthy thing about the course is I don't have a late policy. So if you just joined the class, say on week 2, and you're still getting this assignment 1 worked on, or if just life got ahead of you getting started with the new semester, I'll accept any late work such as assignment 1 for full credit. So get it into me as soon as possible. And if there's any issues sending it through Canvas, it should be open even if it's past due. But if that's not the case, just email me. You can directly email me your assignment at any time, and I'll be happy to accept it through Gmail as well. That's the announcement so far. Any questions or comments at the moment? Okay, the bigger announcement is our first exam is going to be on week number 5. So that'll be on Monday, February 9th. This was always kind of an interesting rundown of things to mention because this is a hybrid class. So I said next week on Monday, this is going to be the very first thing I'm going to be doing is I'll contact every single student in the class individually just to confirm where you'll be testing, giving you the instructions on how to contact the testing center to schedule your exam and those kinds of matters. If you're in the online section, the idea is you'll be testing in either Pocatello, Idaho Falls, or some of those surrounding testing centers, say at Meridian, Twin Falls, Northern Idaho College, and so on. If you're in the in-person section, the idea is you'll just be testing here and now, 2 weeks from today, directly inside the classroom. So we'll talk a little bit more about that as we get closer and closer to the exam. And if we take a peek on the information down here, February or week 4, 2nd to the 8th is going to be ordinary week. But before we get started on this week whatsoever, sometime over this coming weekend, probably on Friday at the best, I'll be updating the information here for the exact chapter coverage on the first exam, as well as review problems. So get a good feel for what does an exam question even look like in this class. We mentioned they're pretty much going to be concept questions, where any kind of outputs that you might have needed through RStudio, whether it's a histogram or a normal probability computation, it'll be on the exam, and your job is really to give me an interpretation on what you see. But you'll see exactly what those questions will look like once we post those review problems down below. So this is where we're at so far. Let me get that back where it was. Any last questions or comments at all, folks, before we get started today? Okay, well, let's begin. We almost finished chapter 2, and I felt like if we really rushed through it and stayed over like 5 minutes, we could have completed it. But I feel like sometimes that's a disservice to this kind of class, so we left just a little bit for today. My goal is to not break a problem like this across a weekend, so sorry about that. We'll try to minimize that from happening as much as possible. Sometimes these questions get kind of long, but this one was maybe just not the best timing. The refresher on the context here is we're looking at the recruitment of population of the rock sole in the Bering Sea from these particular years. This is a data set pretty similar to the one that you worked on in assignment 1 for the seal pups recruitment. We took this information, imported it into RStudio, and obtained these graphics right here. The syntax was really fast, just import through this syntax using RStudio as an assist. And then the box plot syntax was pretty fast as well. Interpretation was pretty quick. We said, for a lot of different things you could have mentioned, we started off by saying, by the 1.5 IQR rule of thumb, we have an outlier in this region right here. So the box plot identifies these for us. Oh yeah, we did say that. Just double checking, we actually said it was an outlier. We have one suspected outlier in this region, and we identified what observation that was in the data set. Because we're using the context, we can't just say one outlier approximately 4,700. We have to say what it means in context, say 4,700 million fish in the year 1987. I didn't say what fish, but again, you don't have to say every single precise element of the context. So you can let some of that facts here carry the work, the fact that it's the rock sole in the Bering Sea. So other thing we mentioned is the median was at just below 1,000 million fish. And this was other observations you could have made. You could have directly talked about the interquartile range, the distance from here to here, captures the central 50% of all observations in that data set. But if it just says mention at least 3 items, then I'm not picky. Anything that you say that's correct on the display you produced will qualify for a good response. Well, the last thing we mentioned was observations are skewed in this distribution. This was tricky to look at, if I recall. This is skewed to the right. You have to kind of turn your head a little bit in that direction till your neck pops a little bit. And notice the axis is moving towards the right. Everything's been rotated. And it's way more spread out in the far right direction. It trails off to the right. So we said we have right skew data for this particular situation. A big part of these notes in chapter 2 was to say which statistic best represents the center value and the spread for the distribution based upon how skewed it is. These are pretty skewed data, very, very compact in this region for the lower half and way spread out in this upper region. So the skew looks substantial. And in this case, we'll measure the spread and the center in this way. For the center, use M, which is the median. And for the spread, use IQR, which is quartile 3 minus quartile 1. We want to explain our choices as well. And one thing I do want to mention about this particular problem is it's out of nowhere kind of a tricky question in an exam setting. You might be given a distribution like this, either as a box plot or a histogram. And when this kind of question comes up, sometimes it's a little vague what we're really meant to do. No matter how careful I am with that wording, it's a tough question, unless you're expecting something like this to come up. So expect to have some problems where you're just telling me what statistic you would actually use to measure center and spread based on the level of skew you see. And this answers the whole question. We'll say, we'll use these. Statistics. Since the distribution is skewed. The direction doesn't matter, it's just a level of skew that's causing the sample mean that we probably would rather use and the sample standard deviation, S, with X bar, to not represent the center and the spread in the way we would like it to represent. Well, any questions at all, folks? Getting just this conceptual question down? Okay, so if this was a real exam question, that's absolutely a problem that can come up. It's a tricky one, so watch out for these sort of things. What I can't ask you to do on an exam is compute this. So I'm not going to ask you to compute by hand, scratch an interquartile range or median. Likewise, I'm not going to ask you to compute a sample mean or sample standard deviation. If those kinds of values are needed for a formula, something like that, then they would be computed and added to the exam itself. So this is more what the exam question is going to look like. But as a homework question, we definitely will do the computations here. So let's be that. This will be our RStudio problem for the day to start us out. I haven't imported the data set yet since I felt like we're all still learning the system. So let's start by importing. Once we get a better handle on this, sometimes I might come to class with the data set already imported so we can jump right in. So let me click on import data set. The next button is from text base. Find the file. This one is example 5. And you can rename it if you like. I'm usually just going to leave it kind of generically the way the file is titled. If we see this information with year in bold and the quantitative variable recruitment, millions bold, then everything's ready to go. Just click on import here. Oh, and by the way, I did learn just the other day that if you do rename the file, definitely don't put any parentheses like that, because it has a way to cause some weird glitches to occur inside RStudio. So try to eliminate any special characters. That was a new one I learned the other day, if you do decide to rename. Underscore, like we see there, is the one thing that definitely won't glitch out. So click import. You get a new window like this every time you import. So just to manage your tabs here, it's probably a good idea to click them away as soon as you know it imported correctly. Click on the play button here, and this is the variable we're analyzing. So we can start off by just extracting that variable. For short, I'll call it REC for recruitment. And the rundown for working with this data frame is you can type its name. I rely heavily on the autocomplete. So I type slowly, hit enter with example 5. Next, to get that variable, again, autocomplete is a big quality of life improvement here, because if I mistype anything, put in the wrong lower or uppercase, I'm not going to get it to run. Hit $, and just use the cursor to grab the right variable, hit enter, and that should run. Hit Control A, then Control Enter to run all the syntax. And if you see these values produced here, then you're on the right track with RStudio. Well, that's our warm-up so far for the day. To actually get our values, though, it's a pretty fast operation. We want the median and interquartile range, so let's compute those values next. First, any questions at all? Just extracting the data and importing and grabbing it. Okay, let me remind myself if I remember the syntax. I believe it's going to be median, lowercase to get the median value. Type inside here, REC, the variable where the red dot is. The next quantity I want is interquartile range. So if everything makes sense here, it should be IQR. I don't recall the case though. Looks like it's uppercase, but again, a big quality of life improvement in RStudio is you start typing, it'll give you the right case for the function it thinks you're using. So hit enter on that to autocomplete, and now it'll run as expected. Throw in the variable once again, REC for recruitment. And now highlight all the syntax, Control A, hold Control and Enter to run it. And those are our outputted values. So let me screenshot this. Mostly just for a reference for me. If you give me work that looks like this, that's okay as well. That makes perfect sense to me. Make sure if you do use a screenshot for outputs that you're only selecting the relevant output. But I'll be always getting in the habit of actually writing these values out. So the medium M is 862.5 million fish. And the interquartile range, IQR, is 1174.25 million fish. Not as worried about the unit, but just wanted the values. But this kind of stuff, saying what the unit really is important if you're giving a response, conveying the context. Well, we did it, folks. That's the finish of the last problem there. The syntax that made all this run is right here. And we're just about done with the notes. I have one more box of summary information to go through, just to tie the ideas together. But any last questions or comments, folks, at the moment? Any questions with the code? Yeah.
So, I'll show you the RStudio screenshot too and the answer, or just
I would say just the answer would be fine, yeah. And really, it's up to your preference. If your answer is just the screenshot, I'm okay with that if you prefer going that way. If you'd like to just type it out, as many people did with your homework, that's a great way to answer it. Or just writing out this way with a digital pen, or if you printed it out with a pen or pencil would be just fine. Other questions at the moment? Okay, well, we went through the rundown of both chapter 1, chapter 2, the getting everyone on the same page kind of material, since we don't have a statistics prerequisite for this course. I feel like I mentioned that a lot, but it's just a good reminder. Last thing we're going to end on here with these notes is just the last major concept of why we're choosing certain statistics over the other versus what is the shape of the data in the very first place, symmetry versus skew. So the information that ties all that together, I think I can fit this on this page here. Maybe. That'll work out. So here's our just summary information for what we've been looking at so far in these notes. We have two different kinds of data sets, symmetric versus skewed. I have skewed left, skewed right, but choosing the statistics is less concerned about the direction. This is more just visualizing histograms for our own information. So if our distribution is at least roughly symmetric, let's emphasize the word roughly there. We're not looking for perfect symmetry. If we were, we probably would never see it with real data. But if our distribution looks maybe something like this, one major peak, it's going to be unimodal, mound-shaped. Maybe has a sort of emphasized direction, maybe slightly more to the right on the skew, but this is certainly roughly symmetric. If this is the case, we would measure the center of this data set using the means sample, X bar, sample mean. And for the spread, we would measure it using S. It's not that the median and interquartile range are doing a bad job. They would also measure the center and the spread. The major idea of why we would choose these statistics in particular is that a lot of the statistical methods we're going to see down the line in this course, starting in chapter 14, 17, and so on, are much easier to use. The methods are more powerful. We'll say what we mean by power of a test when we're using those statistics. If we have to default to something like, say, the median and interquartile range, our margin of errors are going to be wider. The power of a hypothesis test is going to be reduced. It'll just be the best we have to use if the data is skewed badly enough. There'll be more to that story. The sample size is also part of that key there. But for just a generic description, these two statistics would do a good job. If we were to compare them, here, X bar would be pretty close to equal to the mean. Excuse me, the mean would be approximately equal to the median M, which is the 50th percentile. For these data, X bar would be slightly right to the right because it is slightly more right skewed that we can see here. But any questions with that quick rundown for the symmetric case? Okay, now if we say clearly skewed, that's where we go to the different statistics. Center will make the median value on both. For spread, you could cite quartile 1, quartile 3, but if we want just a number that describes a range that's similar to, say, the standard deviation S, which is doing the same thing, we'd more likely give the interquartile range as a value. So IQR on both. If we say it's clearly skewed to the left, the picture might be something like this. Here I'm going to make the skew just kind of massive on this one. So not only is it clearly skewed, but no one would look at that and say roughly symmetric. It's got a massive outlier clear over here, a potential outlier over here. The IQR rule of thumb might flag that one as an outlier. And most of the data is accumulated in this region. Pretend that's a perfectly vertical rectangle there. So this would be skewed left. And one piece of information we discussed before is the mean of the sample, the reason we don't use it for these distributions, is pulled in the direction of the skew. So here, the sample mean X bar will be strictly less than the median M. M is probably somewhere right around here if we calculated it, but X bar would be somewhere to the left. And the more obvious skewed, the more severe the outliers, the further to the left the sample mean X bar would move. And just for the mirror image of that shape, if we say clearly skewed to the right and violently right skewed all at the same time, it could look about like this. Kind of weird data since it's not exactly falling all at once, but then it starts to fall off in kind of an orderly way, almost like a staircase ladder like this. Some data is weird, and this is potential real world data you might see. So here's our clearly right skewed shape. In this case, the sample mean is pulled in the right direction. So that was meant to be an X bar up here on that pane. So don't forget that bar. Let me highlight that. So here the sample mean X bar will be strictly greater than the median. And it's once again probably somewhere out here. We would have to have the real data and compute it, but for a visual, this is about what the situation might look like. Well, any last questions or comments whatsoever, folks, on the chapter 2 material or the wrap up here? Okay, you'll see in the homework that a lot of the questions kind of just boil down to this chart. Which statistics should you actually use to compute, say, a center or a value for spread? And then it'll ask you to compute those values. And that'll be another topic that we'll come back to for a concept question on our first exam. But let's save this up. The second chapter is now considered fully solved. And so the assignment down here, February 2nd, is considered official, 1 week away from today. Let me double check that's right. So occasionally the due dates do move around a little bit just to make sure we always stick to the 1 week rule. The next chapter we're going to be getting into, oops, sorry about that, there we go, is going to be chapter 11, moving into the normal distributions. So if we finish it this week, the due date will be February 4th. Sorry for the random scrolling, there we go. Chapter 11 will be kind of interesting, working with normal distributions. But the major reason we love to talk about the normal distributions in a statistical methods course, or really just any statistics course, is not because the normal distributions comes up all over the place in ordinary data. That's kind of vague if true exactly. The normal distribution comes up in a really, really unexpected way through a whole new object called the sampling distribution. So here we revisit normal distributions again, and this is going to be the major reason why we're going to consider normal distributions. Chapter 13 is essentially going to be the main mathematical ideas that allows our major statistical methods to actually work. This is the basis of where all those methods came from in the very first place. But to get started, we'll be in chapter 11. I gave some information on the reading. We're not going to use the standard normal table. This is kind of an archaic way to work with the normal distribution. People did this hundreds of years ago before they had a TID3. We have something better. Our studio can just rip through these computations really, really quickly. So another topic we'll skip is normal quantile plots, mainly because our author considered this to be kind of an optional topic in his book and doesn't really come back to this very often. So it's an interesting topic if you decide to read it, but it won't be a big part of our course. We'll do checking on normality in a different kind of way. So let me open those notes finally. So to start off with the normal distribution, the unfortunate thing is it's a pretty complicated looking mathematical object. It's a function. And so here's where the calculus that is a prerequisite to this course comes in a certain way. We're not going to do a lot of calculus in this course, but some ideas about areas under the curve are going to be relevant in chapter 11. So if we have a continuous random variable x, that means we're looking from a quantity that came from some kind of numerical quantitative data. We'll say that it will be distributed normally with some mean mu and some standard deviation sigma. So we're modeling a data that has those two statistics. Then we can say the probability model for that distribution x, whether x is referring to, say, speeds of a particular car model, heights of a particular animal, species, and so on, we'll say that this right here refers to X, whatever the quantity is. Tilde means is distributed as, N will be distributed normally, and the mu and sigma here are just going to refer to the statistics we have. So here's the N, the sigma. If it follows the normal distribution, we write the N here. And this whole shorthand is just a quick way to say X follows the normal distribution with mean value mu and standard deviation. All right, STD DEV, the shorthand for standard deviation, sigma. So it's kind of a nice shorthand. This takes a lot of oxygen to say, a lot of words to write out or type out. So this will be a pretty common shorthand that we'll use throughout the course, as the author does in the book as well. Well, if we're talking about this model right here, there's a function that's underpinning how X is distributed, and this is the function f of X. It's a density curve, and some textbooks and probability call this a PDF. So if you've taken probability, that might sound familiar to you. PDF stands for probability density curve. So here's the function. We're not going to work with this directly by hand. I'm never going to ask you to integrate that. That's a monstrous amount of work to get through. But just for the sake of thinking about what the function is, here we have the major component of it is it's a constant multiple of the exponential function. That means this curve right here will never even touch the x-axis because e to the power of anything whatsoever, so a for anything, is strictly non-negative. It's greater than 0 whatsoever. And also look how this is formed. It's kind of strange in a certain sense. We have the mean is a part of the formula here, and a standard deviation goes in these two different places. So the actual shape and location of this curve depends on the model that we're using, the particular choice of the mean and standard deviation. So here's our curve. And if you ever write N01, we'll refer to that as the standard normal distribution. So all we're meaning is the mean will be 0 for mu, and the standard deviation will be 1 for sigma. And this is the standard normal distribution. Any questions or comments about this new object so far? Okay, so aside from the introduction of lots of symbolisms here, we'll come back and use this notation quite a bit to practice it. And the graph we see below, other key facts about this probability density function, or density curve as our author calls it, is the domain of that function is all real numbers. And that's why I could write e to the power of a as positive. Any number you put in there, you can compute it, and it comes out non-negative. The curve never intersects the x-axis. Again, that comes back to, fundamentally, it's just this function with a particular exponent and an interesting constant multiplying it. The calculus side of this is also interesting. The area under this curve is exactly 1. And that's a pretty impressive thought. In particular, if you've taken calculus 1, but not calculus 2, it might be a little vague and fuzzy. But in calculus 2, we learn how to do this particular integration here. The total area under the curve is 1, can be re-expressed by writing. I thought that would stay there. Let's just use the arrow. If you integrate, now it comes back, from negative infinity to positive infinity of, I'll just call this f of x for short, so that function there, you can make sense of this using limits. This is an improper integral, and the area comes out to exactly 1. So we use negative infinity to positive infinity. We're integrating across the entire real number line. And this is what makes it an actual probability density function. If you get probability 1, you've integrated across the entire domain. Because this is a non-negative function, the minimum value when you integrate for any choice of numbers, a to b, is going to be 0. And if you have an interval of positive width, you'll get some positive area to come out. So we can tie this curve down together with notions of probabilities. And that's what this last statement here is saying. Any area under this curve can be thought of as a probability now. So part of the goal of these notes getting started is to say, what exactly do we mean by a probability? By doing some computations, visualizing some of them, and making practical interpretations on the probabilities we get. But this is the topic introduction so far. Again, it's pretty mathematically heavy, so that's one reason that there's a calculus component for the prerequisites of this class. But we're not going to directly integrate things in this class. We're going to make the hardware do the work for us. Any questions at the moment? I think I called for them already, but just in case. Okay, moving on beyond the definition page of the density curve and its properties down below. Example one's purpose is just to think about this kind of information conceptually. Because it's a conceptual question, something like this does make a good exam one type of question. We have a population that we want to model, and we're modeling it using the normal distribution. What I mean by that is, we're not saying the normal distribution is going to describe this population exactly. It's just a tool, and we think it'll give us decent approximations under certain assumptions about the population. It says in a certain population of this fish, it's a herring, it tells us, the lengths of the individual fish follow a normal distribution. So there's a normal model under the background. We'll assume that the population's mean length of the fish is 54 millimeters and that the standard deviation is 4.5 millimeters. To start off this problem, you might want to write down some notes in the margin. It said the population's mean length is 54 millimeters. So we can abbreviate that to mu. We're not using X bar this time because there's no sample. And we're not exactly saying we know the dead-on value for mu. We're saying this is our best guess if we're trying to fit a normal curve to the population. We'll assume mu is 54 millimeters. We're also told the population's standard deviation is 4.5 millimeters. So our symbol there from chapter 1 is that sigma is 4.5. And now part A is possibly one of the more confusing questions. I get a lot of questions about this on homework that can come up. It's extremely important though, because this is a question you should expect to see on an exam setting as a concept question. When we're talking about the probability distribution of X, really we just mean the following. X, well, how's it defined? X is going to be a random variable. It'll denote the length of a randomly selected fish from this population. And we're saying all of the lengths, X, will be distributed. From right here, it said it follows the normal distribution. So we'll use n to say normally distributed. The parameter values we're passing to it are a mean of 54. So 54 will go here. And a standard deviation of 4.5 in millimeters. In this textbook, we always put mu here, and that's pretty standard. And we always put sigma here. And that just kind of depends on the textbook you're working with. Some textbooks put the variance in that spot, so it would have been sigma squared. And if you've gotten into that habit, maybe you've taken a probability course and you've just done that a lot, that's okay. If you squared 4.5, I'll know, and I'll just assuming you're using a slightly different notation, sigma squared there. In our text, we're always going to put sigma, directly as stated, in that second position. And just as a reminder, all this is saying is X is distributed normally with mean, mu is 54, and standard deviation, sigma is 4.5. If you prefer to write it out in just ordinary words, that's totally fine as well. But this comes up enough in the book that it's well worth the effort for best practice just to familiarize our eyes to seeing that, because it comes back in formulas all over the textbook. So it's a great shorthand. Well, all we've done as part A really is just summarize everything they told us up here. They gave us a variable, we've specified the model and the model parameters, both mu and sigma. Next thing we'll do is sketch the graph for the density curve F. And there's lots of ways to do this. If you prefer to sketch this by hand, that's completely fine. Say you printed out the assignment, did it by hand with pen or pencil. If you have digital tools, you can draw this by hand as well, and that'd be totally fine. But we have a pretty big calculator, so one fun way to do this is make RStudio do the plot. So if you prefer to use RStudio, then that'll be a third great option to go. Any questions before we put this into RStudio to do the plot for us? Okay, plotting a function in RStudio is kind of clunky. It's not the best world's natural environment for plotting a function. So I put this in the notes just as a quick way to do any normal plot if you chose to use it. I did make a comment. You ordinarily never want to write the syntax inside of Word, but if there's syntax already in Word, it does copy out nicely and correctly. And I double check my syntax in case the quotations are wrong and so on to make sure you can in fact copy and paste. So let me just copy all of that to do a quick plot. Back in RStudio, let me make sure I reset the environment here. I try to be pretty descriptive for any syntax like this that I'm sharing. It says we're doing a normal plot. Anything after the hash symbol is read as a comment, so we can say whatever we want and it won't mess up the syntax if it's converted to green like this. Instructions say first define the parameters of the model. Here they are, or if we're looking here, they're in this location as well. So mu will update to 54, sigma will update to 4.5, and that's all we have to do to tailor this syntax to whichever example you might be working on or homework exercise. So it says then run all syntax. So Control A with everything highlighted, hold Control, hit Enter, and there's our quick and pretty clean looking normal distribution. The center should be at 54, and yeah, that looks about right. If you go directly up to the main peak, that should be right at 54. So that looks about right. Standard deviation 4.5 means if we go about 3 deviations to the right and the left, that'd be about 70, around 35. That should contain 99.7% of the area. So this curve looks just about right. So I'll hit Windows Shift S to just screenshot it into the assignment. And that would be one way to do this kind of question. Again, you don't have to do this way. If you want to say, put it in a TI-83 calculator, take a picture of it, put the picture in your assignment or email it to me, that works. Or easier to go to Desmos, or a hand sketch will be completely fine as well for this kind of problem. But we've got it. There's our density curve. Doesn't have to be that big, so let's kind of scrunch it down. And part C is just going to finally explain how do we use a density curve like this to describe probabilities. Well, here's how it goes. It says, the probability that a randomly selected fish from this population has a length less than 50 millimeters will be described this way. So uppercase P is the probability set function. We're saying the probability of some event. That event is X less than 50 millimeters. So X is the random variable describing the length of the fish from this population. And that's also the horizontal axis going this way. This axis is length. Let me spell length first correctly. Of a fish from the population. We want to be strictly less than 50 millimeters, and we're told the probability is 0.1870. The nice thing about probabilities is, even if you haven't taken a probability course, just convert this proportion, which is always strictly between 0 and 1, including the 0 value and 1 value, convert it into a percent, and that's a nice way to interpret what you're looking at. It means there is an 18.70% chance, close to 20%, 1 in 5, that if you go to this specific population of fish, randomly select one, it'll have a length less than 50 millimeters. So that's just the occurrence rate for that outcome. Instructions here just say shade the portion of the graph that corresponds to that particular probability. So we're connecting the dots between the probability set function, the graph we see here, which is just an area, which at the same time is also an integral. So let's put this down. 50 millimeters is this value right here. There's a directionality. We're going to the left, so we would be shading to the left on this one. So draw a bar that goes up. Here's our shaded area, and this is meant to be 20% of that area. Keep in mind this way the scale is presented can cause some of the distortion in what you see in the area. Kate says, can you go back to our syntax? Oh yeah, absolutely. Sorry for missing that chat there. So the R syntax to get this graph right here is this statement. Also, you can find it on the notes just down below here, where you'd be changing the mu value here to 54 and the sigma value here to just a 4.5, and that'll make this syntax above run. Any questions about it at the moment to looking at that syntax? Okay, one thing that can go wrong with this syntax is the window size can sometimes cause some weird issues. So if you have a clean environment, everything looks like it's ready to go, and you hit Control A, Control Enter, you'll get an error out of nowhere. That's just because the graphics over here just didn't have a chance to display in the way it ordinarily would have wanted. So this is really a RStudio issue. Run it again with this kind of resized a little bit better. I just have to hit Control Enter now that everything is highlighted, and that error should clean up. So that's the syntax to make all that happen. And in terms of what it produced was just this graph here. We just shaded the area that corresponded to 0.1870 is that area, which is now at the same time a probability. Any questions or comments at the moment? Okay, again, there's lots of ways to convey all this information. We now have the notion that if you have a curve that satisfies the probability density curve requirements, the graph is always above the x-axis, and the area under that graph on its total domain is exactly 1, then these areas are now probabilities at the same time. The way we indicate the probability is just that as a shorthand. But another way to look at all this is we're also saying at the same exact time that probability x less 50, it's an area under the curve, so we can do an integration. The upper limit of integration will be the cutoff value here, right at 50. The lower limit of the integration, well, that'll be negative infinity because we didn't have two numbers that x was between. It's strictly less than 50. And this seems weird because we know these fish cannot have negative length, right? But that's just one of the outcomes of working with this model. The domain is always all real numbers. We'll assume that if this model is doing a really good job, by the time you get close to 0, the curve is so close to the x-axis that the areas are very, very negligible. We're talking orders of magnitude for regions, something like 1 times 10 power negative 50 and so on. So areas way on the negative end are really not giving us any appreciable accumulation. We integrate the curve we see here. I'll just denote it as f of x. And we didn't actually do that integral. This is a complicated one to do. But the calculator is really good at things like, say, midpoint rule, trapezoid rule, Simpson's rule, and so on. So it does an excellent numerical approximation and comes out with 0.1870. So lots of stuff to tie together so far, introducing a probability model like this one. Any other questions or comments at the moment? Okay, here's another weird, interesting issue we get with this probability model. Because this model is depending on area, and it's literally defined through an integration, the hardware RStudio just did the approximation, it means it has issues with if we integrate from a lower bound to the upper bound coming out as the same value. So for another random mathematical fact from back in the day in a calculus class, if you integrate from a to a of f of x, and if this function f of x is integrable, this always has an immediate answer. It does not matter how complicated the function is. Anyone happen to know what the answer should be for that integral there? Yeah, good call, absolutely. If you integrate from the same lower bound and the same upper bound, you will always get 0. Good call on that one. And that's relevant here, and it makes our probability models kind of strange in a certain sense. To get an actual non-zero probability, you need an interval with a length that's bigger than 0. So that means if you try to calculate the probability that x is exactly 50 millimeters, it will always be directly 0, and that's kind of weird. There's a lot of explanations you can give to this one. If you're thinking in terms of calculus, hide that example there. In terms of calculus, a great explanation would be it's because the integral from 50 to 50 of the density curve f of x is directly equal to 0. And this is what we mean by the probability x equals 50. Let's tie that thought together as well, just for completion. And probability x equals 50 is that integral. Integrate from 50 to 50 of f of x dx. So the area comes out directly as 0. This model cannot give you a positive probability on one specific value. It's impossible, and it's kind of weird. Feels like a defect in a certain sense, but that's just the consequence of any continuous probability model like the one we're looking into. Another way to think about it is, here's an alternative explanation. Here's that line, x equals 50, now written as purple. So we can also say, because the area of a vertical line segment is 0, probability x equals 50 is also 0 at the same time. And either answer is just fine. If you want to think in terms of the calculus model or in terms of just a more algebraic view of this, I would take either one as a completely fine answer. So let's call this answer 1 and this answer 2. So we've looked into a lot about the normal model so far without even really using RStudio to find these areas. I think this is well worth our time because once again, we don't have any statistics as a prerequisite to this. We should spend some time just conceptually putting together what is RStudio giving us as a number so we have a picture in our mind. And this is essentially the picture so far. And this is just one of the weird things that happens with this probability model. Any questions so far, folks, with any of these concepts so far? Okay, here's the last weird thing that can happen with this kind of stuff. Let's look at part C one more time. We said probability x less 50 is 0.1870. But you know, one thing that's really weird about this is you could have also said probability x less than or equals to 50 is also exactly 0.1870. And that's weird as well, because sometimes problems have an interpretation of strictly less than 50 millimeters, or maybe we were asking a question of less than or equal to 50 millimeters. Turns out that's irrelevant. And if you think about this, whenever you're integrating from a lower bound to upper bound, there's no way to distinguish whether you're including 50 or not, whether there's a strict less than or less than or equals to. That's not conveyed on these integrals whatsoever. And it's also what's going on here right at 50. Whether you said strictly less than 50 or less than or equals to 50, probability at 50 itself is a dead on zero. And so that's one way to answer that. But that's what part E is all about. It says, explain why probability x less 50 is the same as probability x is less than or equals to 50. And one quick explanation for this one is it's because if you take probability x less 50, let's start with less than or equals to 50, you can break down this probability in a different kind of way. You could say this is probability that x is strictly less than 50, or probability, or x equals, sorry, not probability again, or x equals 50. In some probability textbooks, a union symbol could be used instead because we're implying sets of real numbers when we write out these statements. These are just intervals, and there could be a union taking the place of or. And whenever we have disjoint sets like these that don't overlap, you could write this as probability x less 50 plus probability x equals 50. So across a union symbol, we can turn this into a plus, but the probability that x is exactly 50 is null, exactly zero. So this just turns into probability x less than 50. So the big takeaway thought on this is whenever you're doing a probability or providing a practical interpretation to that probability, whether you write out your words conveying a strict less than or less than or equals will be immaterial. You'll get the same exact probability value out either way. Well, that's the rundown with probability with the normal model at the moment. Any last questions at all, folks, with any of those interesting concept questions so far? Okay, again, this is where a lot of the calculus-based nature in this particular statistics course comes in, but we're not going to do lots of calculus. This is more about the conceptual understanding of areas and integrals that we're pulling in to define the normal distribution. Here's the syntax to do a fast normal plot. Let me just put a border here just to say the last problem has ended. I put down the empirical rule just as another way to visualize a normal distribution. We've cited it already in chapter 2, so I felt like it was a good thing to throw into the notes as we see it here. So here's our normal curve. And if we have some particular mean mu and standard deviation sigma as parameter values, this gives us an idea of what is the standard deviation actually doing in terms of defining the spread. So 68% of the area under the normal model is within one standard deviation of the mean. If we go 2 deviations, we're capturing 95% of the area. And for 3 deviations, we're capturing 99.7% of the area. And some statistics courses, we would actually do a problem just like this. But once again, we have a powerful calculator that goes and gives an approximation way better than 1 percentage point approximation that we see here, or decimal point rather, of a percent. And so this is just another conceptual way to look into the normal distribution. So what a real question might look like for this particular chapter would be this. Oh, hang on, I'm not there yet. These are more concept questions still. A real question would be this one down below, but I forget there's also a great thing we have to discuss of when do you use the normal model in the first place? Chapter 13 is going to be surprising for doing a statistical method, and we're modeling a sample mean. But for analyzing individual members of a sample, it's an important topic to know, can you use the normal model or not? So here's data that we've seen before. When we analyzed these data, we said that this was skewed to the left because it's more left-leaning with the main peak here. and data trailing out just slightly more to the left than the right. The question is it reasonable to model these data? These are number of nerve cells in a cross-section extraction of the block of tissue from the intestinal wall of a pony. But if we were going to model this with a normal distribution, really the major idea we have is, can you fit a curve that's 100% symmetric and mound-shaped to these data? I would say, well, maybe not perfect, but that curve might not do too bad. So the curve might look like this, for example. It's not going to be perfect because it's real data and it does have a little bit of skew to it. But I would say here, yes, it would be reasonable to model the number of nerve cells from this pony's intestinal wall. We'll say yes, because these data are roughly symmetric. They have one major peak where the data accumulates, so we can say it's unimodal. In other words, one peak. And it's also mound-shaped, or bell-curved, if you prefer to say. I'll go with mound-shaped. That's an important distinction because it's plausible that your data could have looked like this. You can get data that looks like this if you're essentially just taking a random sample of random numbers between 0 and 1. This shape is going to occur. The heights, I'm trying to draw to be roughly close to each other, but not perfect. This is uniform and not modeled by the normal distribution. The trouble is, if we try to take this curve and fit it to these data, no matter how you resize this, it's never going to look right. There's always going to be regions where it just didn't fit in too well, regions where we're saying that area is concentrated there, but it's not. That never looks like a good fit. So the normal model just doesn't do a good job to that data. But it does okay here. Not perfect, but acceptable. Maybe if we had a larger sample, more than 23 sections, we'd have a better sense of the shape of these data, and the curve would fit a little bit better. But even from a population that's perfectly normally distributed, if the sample size is low on the lower end, say 10, 15 observations, you're going to get a lot of pictures that look like this. So these are the good cases. This is when the normal model is going to work out, at least roughly symmetric, and more symmetry is better. We say things like mound shaped because we're not looking at flat. The normal curve doesn't do a good job here. And we say unimodal because there should be one major peak that lines up with the peak of the normal curve itself. So here's one case where the data looks really bad, but any questions so far before the part B? Yeah.
Question, if it has like kind of two peaks, but it was still somewhat symmetrical, would that still work?
It wouldn't work at the way we would want it, but what we could do is, if there's two main peaks, sometimes there means there's a categorical variable somewhere in the background of that data. Maybe one peak is for one particular, say, brand of cereal for looking into sugar content. The other peak is for a different brand of cereal. What we would do is separate out the data that corresponds to one brand and another brand and model using two different normal distributions, one for each peak we saw in that distribution. Other questions with that so far? Okay, so aside from bimodal, it is a challenge because we are potentially modeling two different kinds of things. Uniform is also a challenge because our normal curve doesn't have a flatness aspect to it. The next big challenging data is highly skewed data, like this one here. And this is kind of an interesting problem. It says VO2 max is the maximum rate of oxygen consumption obtainable during physical exertion. So you might have this measured if you have a heart condition, for example, or maybe you're an elite athlete and they're just seeing the effects of training. It says next, a VO2 max value provides a quantitative value of endurance fitness. Low VO2 max is below 30, just to get a sense of the scale here. So if you're below 30, it's kind of on the low end, maybe not super fit. And elite athletes, so imagine someone who does, say, cycling competitively, have max values that are above 80. And this is a made-up problem, but for kind of an interesting scenario, let's say we're analyzing the fitness of a local cycling club. You measure the VO2 max for 15 cyclists. They're humongous enthusiasts, so they've wanted this done. And this is the histogram of the sample data. It's kind of a casual group, but it looks like we have like one elite athlete that's a member of this club, just kind of killing it out there. And the rest of them are just kind of typical people. They're above 30, below 60, so they're pretty fit. If we want to model this with a normal distribution, we would not be gaining anywhere because the normal curve to this might not look too bad going to the right. Here's the shape. The normal curve is completely symmetric. So if that's your shape going to the right, there'll also be the shape, if I can try to mirror that, there'll be the same shape going off to the left. And there's no data out here to the left. The normal curve is doing a spectacularly bad job modeling these data in this case. So here we'll say no, because these data are significantly skewed to the right. So the normal model shouldn't be used for these data. There's other probability models that could work. The exponential model would do a better job. Other models also capture skewness. We'll look into a chi-squared probability model later on in the course as well. But any last questions or comments so far, folks? Okay, that was a lot of conceptual work doing this so far. For the computational side, that's what the next examples are going to be all about. So let's take a look into those next problems. This one's based off pretty old looking data. It says it came from 1993, but it's a pretty interesting problem to think about. Here's the overall context. The time it takes a driver to react to the brake lights on a deaccelerating vehicle is critical to help avoid rear end collisions. So that just sets the tone for the context we're in. Getting closer to what we're actually doing, we're looking into the article, Fast Rise Brake Lamps as a Collision Prevention Device. In that article, it suggests that the reaction time, this seems to be the major thing we're thinking about. The reaction time for an in-traffic response to a brake signal from a standard brake light can be modeled with a normal distribution, so the normal model is in play. The mean value of 1.25 seconds. Oh, geez, sorry, that doesn't work. Mean value of 1.25 seconds. And a standard deviation value of 0.46 seconds. So that's our context. This was in a controlled setting, so you can imagine some weird driver's ed rig where you're just looking at a computer in front of you, probably a realistic car interior, and you're just responding to the brake light you see right in front of you. That said, on average, people responded in 1.25 seconds to the brake light. So that's mu. The mean is quite large. It's never the full story for the data. The standard deviation in the context of reacting to a brake light, that feels large too, 0.46 seconds, almost a half a second. So sigma is 0.46 seconds. Here we have a variable. X will be the reaction time for the in-traffic response to a brake signal in the standard brake light for a randomly selected driver in this particular study. We hope we can extrapolate this study to, say, drivers in Pocatello or drivers in Idaho Falls. But for the moment, we're just modeling the data that we saw in the study itself, much like, say, trying to model the VO2 max data that we saw in the last example. So in order to actually model these kind of data, the very first thing we want is the probability distribution of the variable x. Again, this is always kind of a confusing question when it comes up. And you do have a lot of ways you can write out this answer. You could say x is distributed normally with a mean 1.25 seconds and a standard deviation of 0.46 seconds. But the way we'll often write this down is, if you see probability distribution, we'll write out x is normally distributed. The mean is 1.25 seconds. And the standard deviation sigma is 0.46 seconds. And I didn't put any, I don't know why I put sigma there. I didn't put any units in there, but if you feel it's kind of helpful for interpreting the context, no harm in capturing the unit as well. I only put it on one, but the nice fact here is the unit for the mean and the standard deviation will always be identical. Here, we're doing our first probability computation for the course and for the day. But the major work is giving the practical interpretation once we have the number. So here's the probability set function. Probability that x, peak reaction times, is between 1 second and 1.75 seconds for all drivers in this study. The way we'll compute this is we'll write out in our syntax p norm 1.75, then give the value for mu, the value for sigma, and this will give the area to the left of 1.75. But we need to stop right at 1 second, so we also have to subtract p norm 1.00, or just 1 will do the job. Give the same parameter values, 1.25, 0.46. So using RStudio as a calculator, this is really all you would have to write. Let's go and grab RStudio now. We can kind of compact this because now we're basically going to use it as a calculator at this stage. I'll hit Control A and delete. Let's get a clean field going here. We'll restore some new values over there. But you know, a good way to use this is not necessarily to type it all out directly, because if I have to type out 0.125 comma 0.46 over and over again, I guarantee you I'm going to make a mistake. So probably a better thing to do is go back to the model. Define mu, I'll just type it this way in ordinary words, gets the value of 1.25. I'll write sig short for sigma, gets the value of 0.46. And if these two stored, everything we do down below is going to work a lot faster. I'll say what part we are on, part B. And here's what it looks like just typing this into RStudio. P norm 1.0, or excuse me, 1.75. We have to do the upper bound first. Then just type mu and sigma, and it's going to cite the values you defined above. Then go minus P norm. Now we're doing the lower end, coming from this side of the probability function, P norm 1.00, mu and sigma. And again, the 0.00 is irrelevant, but just makes it feel like we typed it in exactly. If we run all this, we should get a good picture, or excuse me, a good probability. And here it is. This is the entire output. It didn't say what to round to, but when it comes to probabilities, 4 decimal places is a pretty standard all-purpose value to go to. So I'll write this out as a 0.5681. So we got it. That's a really fast way to do that computation. RStudio is pretty convenient, but again, I'm not too picky for the systems you use. RStudio just gets more and more convenient as we go throughout the semester. Say doing statistical methods are extremely fast in the system. But if you know how to do this in a TI-83, 84 calculator, and so on, and you just prefer to do it that way, no harm done. But if you want to do everything in one environment, it's as fast as this. We got a number out. All we have to do is interpret it, but any questions at all getting the number? Okay, now once we get down here, if this was a, say, real exam 1 question, I'll just say the probability x between those values equals 0.5681. And the whole question for you would be this part right here, interpreting the value you got, the probability, in context. So here's the interpretation that we could put down as a pretty generic way to think about this. You can leave this as a proportion or a probability that's the same number either way you think of it. But I think for interpretation, I personally like to make it a percentage. So I'd start off by saying there is a 56.81% chance that, well, what we do next is we go inside the probability function, the interpretation's on X, but we have to remind ourselves what it is in context. So I'll say that the reaction time for a randomly selected driver and then it's a randomly selected driver for the study and it's a reaction to a brake signal. But again, you can be a little bit brief unless the whole question happens to be anything specific about that information. But I think when we say reaction time, we're all thinking to the brake light signal. Well, there's a 58% chance that X is between those two values, 1 second and 1.75 seconds. So we'll just say verbatim is between 1 and 1.75 seconds. And then that does the job for us. That's our practical interpretation, and that's a probability that we computed. Let me just convey that's the interpretation there with an arrow. Any questions at the moment, folks, getting that value? Okay, so these go pretty fast. For example, if you were doing this last one, let's see, let's make sure we don't get too close to the end of the time. I don't want to run over. But if we were to do this last one right here, all we would have to say for this one is P norm to 1.25, or mu if you decide to go that route, 0.46, or sigma. But then we have to be a little bit careful with this one. RStudio, the reason I had to subtract this way is by default, it wants to take the area to the left of a particular value. So if I go like this, it's going to do the area to the left of 2. We want area to the right of 2, more than 2 seconds. So we add just one more description. Lower dot tail equals false. So that'll do the computation there for us. And again, don't know why I did that. The major reason we went lower dot tail is false. Let's go with maybe this color. It's just to capture the right-hand direction we see there. So putting this back into the syntax, here's part C, and we compute P norm to mu sigma lower dot tail equals false. So that should do the job for us. And it's a pretty important computation, because if you run that and get this probability, it's small, but it's non-zero. And this is someone taking more than 2 seconds to react to the brake light, 0.0515 equals 0.0515. Maybe double check my numbers. Okay, then for the interpretation, we'll say there is a 5.15% chance the driver takes more than 2 seconds to react to the brake light. And that's significant. That's about 1 out of 20 trials randomly selecting these drivers. So it's something to think about if you're driving home this afternoon sometime later. But any last questions so far at the moment? Okay, when we come back on Wednesday, this is what we'll be doing, some more probability computations. We'll be looking into the full suite of things you might have to compute at any point in this semester for normal models and how it ties in with the graph. And then another problem with just more scenarios. This is one that's about snow. And again, if this computation seems kind of scary in a way, also remember it's a normal model. It's just our best estimate of reality. And this was for drivers that they were around 1993. So populations also change with time. So here, the 5% chance to really get that to be accurate, they would have to just redo the whole study from ground up. But have a great afternoon, folks. We'll return here on Wednesday's class. Take care.